Swayam Prabha. Digital India. Educated India.
Students, so we meet again. Today we have the third lecture in the series of lectures on consolidation and settlement. As always, we shall first review a little bit of what we have discussed in the earlier lectures and then go forward with new material. Let us take a look at the next slide. So, as this slide shows, in the last lecture I introduced the phenomenon of consolidation, shorn of all mathematics, just the basic physical phenomenon that takes place, which is responsible for time dependent settlement or compression, and that is what is known as consolidation. Briefly speaking, we saw that consolidation is a gradual phenomenon of compression which takes place due to gradual expulsion of water from the voids of a saturated soil, and the soil usually is clay. As we discussed last time, it is clayey soils when saturated which exhibit predominantly time dependent compression in view of the low permeability or the low coefficient of permeability of these soils, which are in the range of say 10 raised to minus 6 to 10 raised to minus 7 or minus 8. Now, in view of this kind of compression taking place with time, we have two questions to be answered. One is, what is the likely compression when a building is constructed on such a clay, or for that matter in general when a load is applied on the surface of such a clay layer, what is the likely maximum compression, the total compression or the ultimate compression that is likely to take place. And not only that, which is probably of greater importance, is the rate at which this settlement takes place. So, we got into discussion of the first part of this problem, that is the computation of the total settlement. The computation of the total settlement is important because we can't afford to design a building and take a chance and see how the compression takes place, because during the process of consolidation or compression, if the building is unable to adjust to the degree of compression that takes place, it is not possible to do any mid course correction. A building is not an object where you can do any changes or alteration or rectification while the settlement or consolidation is taking place during its lifetime. In view of this, it is important therefore that we have a method to compute this possible compression or consolidation beforehand, before an activity takes place, that is before a construction or before application of load takes place. We should have a method to compute the likely compression or the total consolidation settlement that is going to take place, and unless we know this, we cannot possibly adjust the stress that is transferred to the soil due to the building, thereby save the building from possible excessive settlement and possible distress. Okay, then in short, therefore, we need to know how to compute the total settlement that is likely to arise due to a construction or due in general to a change in stress. So, if there is an increment in stress that is existing on the soil in the normal conditions, then a compression is going to be induced and we need to know how much this compression is going to be. It is also therefore of importance to know in what time this will take place. Theoretically, ideally speaking, it will take infinite time. This compression is a time dependent phenomenon which will go on, but from a practical point of view, most of this compression, almost entire compression or about 95% of the compression takes place within a certain time duration. So, within the lifetime of this building, how much is the compression that is going to take place and at what rate it is going to take place is of great importance. We will be in a position to see the computation of time rate as well, but to begin with, let us spend a little time on the computation of the total settlement. We saw to some detail the computation of the total settlement last time. We even saw a numerical example. To put it briefly, we said that this compression, the total compression that is going to take place is dependent upon the change of void ratio, which let us say is E0 to begin with and changes to E final during the application of a load, which in terms of stress may be considered as sigma 0 initially, sigma 0 dash if we consider the effective stress, and which increases to sigma final effective. Why we are considering effective stress? Also, we discussed in the last lecture, the explanation for this is that it is the effective stress which is transmitted ultimately to the grains of the soil solids, and that is what is responsible for the actual compression or the change in volume that takes place. As we discussed last time, initially when the load is applied, since the solids are incompressible, they do not take any of these loads. The loads are first getting transmitted to the water, but water being also incompressible does not take the load. However, it is able to move out from the voids of the soils, and therefore, the load which comes on the water gets transmitted immediately to the solid grains as the water moves out, and this causes the solid grains to readjust themselves, reorient themselves, move, and then or make up a more compact or more compressed volume of soil, and this compression is what we are planning to compute. And since this is essentially due to the stress that is transmitted to the solids or the grains, we shall be computing the effective stresses and their relationship to the void ratio. Let us proceed further. So, we saw in the last class that if we apply this principle, we can compute the total settlement that will take place in terms of the total void ratio change that is going to take place. Since this settlement depends upon the thickness of the soil layer, we need to compute the change in volume or change in void ratio per unit volume, which is the same as saying per unit thickness, since the area remains constant during compression, and this when multiplied by the actual thickness of the layer will give us the total settlement. So, if you look at this formula, we have a term here which is change in volume or change in void ratio, that is change in volume is expressed in terms of change in void ratio, since the volume of the solids as shown here remains constant, and per unit volume, unit original volume will tell you how much is the settlement that takes place in the unit thickness of a soil. This multiplied by h, the actual thickness of the soil, total thickness, will tell you the settlement that is likely to take place in this total thickness over the total thickness of the clay layer. Okay. So, this is the settlement, and this requires the computation of initial and final void ratios, as we just now saw. How do we get these void ratios? We can get these void ratios by conducting a test. We also saw the name of this test and some details of this test, that was the odometer test. Now, once we know the fact that the settlement depends upon initial and final void ratios, since the initial and final void ratios are effectively caused due to the stress changes in the soil due to application of external loads, we must relate these void ratios to the stress changes. Thus, if we want to know E0 and the final void ratio EF due to application of certain external load, we must know the linkage between E0 and EF and the initial stress sigma 0 and the final stress sigma f that is going to arise due to the application of the load. This expression which I have written here is in general terms. In particular, however, while calculating the settlements, we will be dealing with not just sigma 0 and sigma f, but the effective stresses sigma 0 dash and sigma f dash. So, this means that we need to establish a relationship which can be called as sigma E relationship, the stress versus void ratio relationship. In general, it will be a stress change versus stress void ratio change relationship, but then we can always express it in terms of the applied load and the resulting stress change. Let us take a look at the next slide. So, now over and above what we had discussed in the previous lectures, in today's lecture we shall be dealing with how to relate this stress with the void ratio, or with the void ratios with the applied corresponding stresses. Then we shall see in general how compression of clays takes place, what is the type of E and P relationship, and how we can describe these in terms of certain compressibility parameters. And then of course, we shall see what we have been talking about, that is the theory of one dimensional consolidation. Let us go back briefly to the consolidometer or the odometer. We know that in this we will have a soil specimen bounded between or sandwiched between two porous sandstones inside a container filled with water. When we apply a load, drainage takes place, the water in the soil specimen oozes out, is expelled through the porous stones, and the soil specimen compresses. And a typical odometer test consists of measuring this compression. What we do there is, we have this dial gauge. We can measure the compression that takes place in the soil specimen in terms of thickness change. Suppose this is the original thickness of the soil specimen. The thickness, let us say, is h. The change in thickness, say delta h, that takes place with every application of load increment can be calculated, can be in fact measured. So, there is this dial gauge which keeps on measuring the change in thickness. So, we can take readings of this dial gauge, readings of this compression at different time values. So, effectively in a odometer or a consolidometer test, the output that we get will be in the form of a table in which we will have time starting from 0 to various different values and the corresponding change in thickness, or in other words the initial and the final dial gauge readings, which in turn will help us when in terms of their difference to compute the change in thickness which we are interested in. So, if the initial thickness is h, the initial dial gauge reading is, let us say, D1, D0, and the first dial gauge reading is dF due to a particular load increment, then the difference between these two will give you delta H. Now, how and when do we know that we have to take the final dial gauge reading? Normally what happens is, when you apply a stress, the compression phenomenon starts taking place. This compression phenomenon, as we have seen, is time dependent, and that is the reason why we are looking into this phenomenon so critically, and it, theoretically speaking, goes on taking place indefinitely. But then from a practical point of view, the dial gauge reading, which in fact depicts the compression, becomes steady after a certain period of time. Suppose you apply a load of, to begin with, let us say 0.5 kg per centimeter square on the soil specimen. There will be some initial dial gauge reading which will correspond to the initial thickness of the soil specimen. Now, when you increase the stress, the specimen thickness decreases, and therefore a new reading arises, and this reading will go on changing with time. At some point of time, usually after 24 or 48 hours, this change in reading is so small that the dial gauge cannot possibly measure this change in reading. The dial gauge starts showing a stable, somewhat stabilized value of reading, and it is therefore important that in situations where the dial gauge reading is very small, we must be able to measure it very accurately, which means that we need a dial gauge of very high accuracy. The least count of the dial gauge must be such as to capture even small changes in thickness of the clay specimen. Usually we use a dial gauge with a least count of 0.001 inch or millimeter. This is sufficient enough to capture the change in thickness that takes place with time, and when the thickness change and correspondingly the dial gauge reading reaches a level which is below the least count of the dial gauge, then the thickness will appear to be steady or unchanging, and that is the time to apply the next increment of load. So, we apply one increment of load, wait for the dial gauge readings to stabilize. This might take anything from 24 to 48 to 72 hours depending upon the type of clay that is in question, that is being tested. Then we apply the next increment of load and repeat this process with every increment of load, and for each increment of load we will take readings from time t equal to 0 to a certain value of time, maybe 24 hours or 48 hours, and go on computing the change in thickness. Now, this is effectively what we get from a typical consolidometer test. From this we can compute the void ratio. Once you know the change in thickness, since the change in thickness is essentially due to change in void ratio, we shall be in a position to easily compute the change in void ratio E1 minus E2 as a function of the change in thickness. This void ratio change, since it is taking place due to a certain increment in stress, we can also know what is the change in stress and what is the corresponding change in void ratio. Change in thickness will lead to change in void ratio, and it is this information which is going to be of importance to us in computing in advance what is the change in thickness or settlement that is going to take place when a certain load increment is created due to the application of an external load in the form of a construction activity. Okay. Now, this graph shows typical compression behavior of clay and sand to emphasize once again why we are particularly interested in computation of the settlement in clays only. Look at this graph. This shows how the compression takes place with time. Here the compression is expressed in terms of percentage of the total compression that takes place for any given load increment, and you find that even after 60 minutes this clay layer is showing considerable rate of compression. In fact, in practice it is not in 60 minutes, this